Welcome to Algorithm Seminar. Today, we're very happy to have Insu here. He's a postdoctoral research fellow in the Department of Electrical Engineering at Yale University, hosted by Professor Amin Kabasi. He obtained his PhD degree at the Korea Advanced Institute of Science and Technology in 2021 under supervision of Professor Jingwoo Shin. He was a recipient of Microsoft Research Asia Fellowship in 2019. His research interests focus on approximate algorithm design and analysis for large-scale machine learning problems and their applications. Please welcome our speaker.
Hi everyone, my name is Insu. Yeah, I'm the postdoc at Yale University. So today I'm going to talk our work, fast neural kernel embeddings for general activations. So this is joint work with wonderful collaborators, Amir, Jaehun, Roman, Lichao, and Amin. Yeah, this is the outline of today's talk. So is it this screen sharing?
Yeah. So infinity-wide neural network plays as a Gaussian process. I picked this figure from the Google blog. As this figure shows that if the width goes infinity, the output of neural network can follows the Gaussian distributions. And this limits is very useful for model the training dynamics of neural network. So suppose we have a network promised by theta, and it takes the vector d-dimensional vector x and output a scalar. And so this network is trained by minimizing the squared loss through the gradient flow, which implies that the parameter change is in the direction of the loss decreasing. So with simple calculations, okay, this parameter change is inner product between the tangent line and the difference between the predictions. We can also find the change of the predictions can be described by some kernel functions. Here we call this kernel tangent kernel because it is defined by a tangent line of the neural network output. When function f neural network, we call tangent kernel neural tangent kernel, NTK for short. Interestingly, when width goes infinity, the tangent kernel does not change over time, and it does not change over time and becomes static. Okay? And it remains the same as the initialization. This is with these observations, this makes the predictions are equivalent to the kernel regression with the NTK, and this is very useful in analyzing generalization, optimization, regularization of the neural networks. Okay, so we call also the output of infinity-wide neural network follows the Gaussian process with zero min, and the covariance function is characterized by these kernel functions called neural network Gaussian process, NNGP for short. We call neural kernel NTK and NNGP neural kernels. So particular these kernels depend on both depth, network architectures, particular depth and activation. And the parameters does not change these kernels under the infinite width limit. Okay, so most of infinite width neural kernels are mostly focused on ReLU activations. However, practically, ReLU is not the best choice. For example, for 3D objective and sound modeling, the sinusoidal activation sometimes performs better. So as this figure shows that when we model the 3D reconstructions, the left side, which is the sine activations, describes the high frequency and the better performance. And also in transformer, the ReLU and Swiss activations, which is kind of smooth version of ReLU, are more frequently used. So in this work, we focus on the questions: what are neural kernels of general activations? Okay, our first contribution is to find the explicit expression of neural kernels for general activations. So we can fill this table There are some activations so for some activation only NNGP are known, but we can find some expression of NTK of these some activation functions. And for Gabor and polynomial activations, we can find both NNGP and NTK kernel functions, which were not known before. Okay. So we can compute the exact or approximate of kernel functions. Our second contribution is to approximate this kernel matrix using the sketching algorithm. In particular, we want to approximate this n by n kernel matrix in a form of low rank, so that using these low rank structures, we can solve the kernel method very efficiently. In particular, for homogeneous activations, we can guarantee homogeneous activation with some assumptions. We can guarantee subspace embedding property, which means that our low rank approximations preserve some spectral properties. Okay, so practically we can observe up to 100 times speedup compared to the exact computations, and all code can be found in the page of this official Neural Tangent.
So this might be unrelated, but what kind of models are this when you say? When you say 106 times speed up,
yeah.
Is it for like I don't know, transformers or?
It's convolutional. Yeah,
Convolution?
Yeah, CNTK. I will explain details in the later page. So let's move to the exact kernel computation. Okay, so it's good to start the simple examples, which is the two-layer neural network. So for these examples, we have two type of parameters, WL is the second layer, and W1 is the first layer. Okay, so by definition, the NNGP can be expressed as this expectation form, where W is a standard normal Gaussian vector in dimension D, which is same as the input. And NTK also can be computed when you do some calculations of the derivative of f and plug into the definitions. And it is a product of inner product xy times some kernel functions in red box plus NNGP. So to compute neural kernels, we need to know what these kernel functions are. Actually, these kernels is so-called dual kernel, which is defined that for input x and y, the d-dimensional input, and we consider a smooth function, a scalar function, sigma, and here we just assume sigma is a smooth. But yeah, then the dual kernel is defined the expectation over random Gaussian vector, standard normal Gaussian vector of the product of sigma, and the input of sigma is the inner product of W to input. So for specific choice of sigma, this dual kernel can be computed with the closed form solutions. For example, for ReLU, the dual kernel is arc cosine kernel, and sine cosine exponential activation, its dual kernel can be Gaussian kernel. I just want to note that this dual kernel actually function of radius of input and their angle, more specifically the cosine of their angle. So we can simply write this k sigma to the some small kappa sigma takes the norm of x, norm of y, and they're in a product scales norm. In particular, this can be expressed by expectation over two-dimensional Gaussian variables, where the covariance function is defined by some inputs. This is simply derived by some change of variable techniques. So the question is, what is a closed form expression of the dual kernel? We first answer these questions for when the activation is polynomial. Suppose the activation sigma tilde is a degree polynomial, and then each dual kernel is also polynomial in the cosine of angle, and their degree is same as a Q. And here the radius of input and activation only affect the coefficient of this polynomial here. So moreover, if this polynomial is tightly approximate our target activations, which is not possibly polynomial, then the corresponding dual kernel can be also is also similar and close to each other. So using these observations, we can compute the dual kernel and dual kernel of sigma and dual kernel of sigma prime. And with this, then we can compute the NNGP and NTK of two-layer neural network. And this approach can be naturally applied to more deeper layer, because we have a deep depth L layer, depth L neural network here. And it is known that following the recursion, neural kernels are known, where to compute NTK in L layer, we need to compute the two additional kernel functions. Here, actually, these two kernel functions in the red and green one is dual kernels, and the red kernels can be computed by applying the previous NNGP values to the sigma prime K prime. And similarly, these the kernel values in green one can be applied these NNGP kernel values to kappa sigma. So to summarize, once we have a dual kernel, so we can using this and recursion of neural kernels, we can compute depth L, NTK, and NNGP functions. However, one thing I note that is that there is a NNGP with some following dual kernels. It's reported that this NNGP regarding this dual kernel outperforms other neural kernels with known activations. But this is a practically reported that this NNGP performs very well. But the problem is that activation is unknown, so we don't know what activation corresponds to this one. So using these observations, we can compute the NNGP, but to compute the NTK regarding these dual kernels, we cannot. It is unclear to compute NTK, because for NTK we need to know about the K sigma prime. Okay, so here to solve this, we find some relationship between K sigma prime to K. Formally, if we have K sigma, then we can transform this to kappa sigma, and we just take a derivative with respect to its angle and divide it by the norm, then that gives you a K sigma prime. Hence, even if we don't know about what the activation is, once we have a dual kernel and we can find it's some kind of derivative form, then using these recursions, we can obtain the NTK and NNGP kernel functions, the closed form formula. So using these observations, we can fill the missing kernels in NTK, where this type of kernels, this type of kernels only know the NNGP kernels. But using these ones, we can easily find what NTK. So this is the first section about the computing the kernel functions, and now I will move to the approximating kernel values, kernel matrices. Okay, so the previous result, we can get kernel functions. But more formally, if we have n of data points, this gives an n by n matrix. However, practically, computing the n by n matrix is very expensive. For example, the convolutional NTK with Cypher 10 takes over 1,000 GPU hours. And even if we have a kernel matrix, n by n kernel matrix, solving kernel problems using this kernel matrix requires the cubic time. And for large n, this is very, very infeasible. So we try to approximate this kernel matrix in the form of low rank approximations. So with these low rank structures, the kernel regressions and other kernel method can be solved very efficiently. And we want the rank of our approximation is small as possible. It's sampled linearly. Okay, so to solve this, we first consider a homogeneous activations, which implies that any scaling factor in the input can be extracted out of the activations with absolute value. Then it is to observe that the corresponding dual kernel can be represented some normalized dot product kernels. which means that if given input x and y can decompose into norm of x, norm of y, and there's some scalar functions who takes the cosine of their angles. And for fully connected deep neural network, this holds for NTK and NNGP. Okay. For NTK, for NNGP, the angular function is simply L-fold composition of this dot product kernel kappa. Okay, so we can compute by composition this kappa to get a NNGP. And for NTK, looks a little bit complicated, but it's simply linear combinations composing composition of the kappa and its derivative. So since they are scalar functions, then we can obtain these functions very fast, very efficiently, very fast. And so I'm gonna explain our high level of our result. So under these settings, we can find some low rank psi here, where its rank is m. And if m is dimension is chosen by these values, we can guarantee some subspace embedding guarantee in terms of the exact NTK in depth L. Here, I just want to mention this: the rank or feature dimension m depends on the f lambda, which is defined as a statistical dimension. Statistical dimension of the exact NTK matrix, and this is typically this is no greater than the rank of the NTK matrix, and practically this is very smaller than the rank. And indeed, this statistical dimension, this is statistical dimension. So when we think of the randomized projection matrix, the rank of the value of m, the statistical dimension is optimal to approximate to guarantee subspace embedding of the original matrix.
How does it scale with L?
Oh, L is the
Depth, right?
Yeah, depth of the network.
How does it scale? How does S scale with L?
Yeah, so it scales q to the power L. The rank is a q to the power L.
Okay.
And we consider L is constant, then this this is a polynomial in Q, which is the so what is Q? So Q actually requires additional assumption that the dot product the dot product kernel function can be tightly approximated by degree Q polynomial, and the approximation errors should be less than 1 over poly n. And since this is some scalar functions, we can control their approximation errors. Okay. So then by choosing the feature dimension, statistical dimension times some polynomial term in Q to the power L and log n divided by epsilon squares, we can guarantee the subspace embedding. And computing these psi, constructing these low rank features, the runtime is sparsity times n multiplied by statistical dimension times some additional factor. But mostly this is a strongly subquadratic and can be linear in n. So for some simple example, if kappa is some exponential functions, which is the exact case normalized Gaussian kernel, we can choose the degree very small numbers. So for example, the log n. Then the rank or feature dimension can be s lambda times some polylog of L, polylog of n, and this can be, if L is constant, this is an optimal feature dimension for the subspace embedding, as the random projection it is. Okay, so this is our one result, and now I'm gonna explain the high-level ideas. So indeed, our key observation is that NTK and NNGP under the homogeneous activations and fully connected neural network, they are normalized dot product kernels. So our first approach is that we can approximate this dot product kernel function f by some polynomials. Let's say this is polynomial approximate by polynomial degree q, and where the coefficient is Cj. Then this gives us the neural kernels as a mixture of polynomial kernels. Okay. And for polynomial kernels, there's the trivial feature map, which is high-order self-tensor. So this polynomial kernel actually x inner product y to the power j is exactly same as the inner product of the self-tensoring of each input. Okay, so with these observations, we can construct feature map of neural kernels by stacking every self-tensored features with multiplying the square root of CQ coefficient. Okay. Here, if whenever f is a positive semi-definite matrix, the coefficient in its Taylor series expansion is always non-negative. It is a known fact in prior. So that means we can easily find the non-negative coefficient CQ using the Taylor series expansions of f. So the entire feature is valid values. However, the problem is that the tensor operations leads to exponential dimensions. For example, these constructions gives us d to the power q dimensions. So this makes an additional computational issues. So to solve this, we tend to use sketching. So sketching is actually dimensionality reduction techniques, which is effectively used for the tensor operations. So more formally, we want to find some random matrix which projects the d to the power q vectors to some smaller vector, while its inner product are approximately preserved. Okay, so given x and y, we want to find the q, pi q, and pi q maps these to smaller dimensions, m here. So in particular, we use a recent technique called oblivious sketching. So actually, it's kind of sketching, but I will, as high-level explanations, it sketches only inputs only order of 2. Because one can also try sketch the input of input, which is the tensor productions of order q. But sketching, the variance of sketching is exponentially large in terms of the order. So to avoid exponentially large variance, this work takes only tensors of order 2. And these variances can be controlled by selecting the output dimension m. Then the entire variance are not exponentially large. They can be controlled by some polynomial. Okay, so this is the formal result of the oblivious sketching. So the point is that they need some polynomial. They need a feature dimension, which is the polynomial in Q, which Q is a degree, and there's a statistical dimension S. And the runtime to compute the sketched feature is also polynomial in Q. It's Q to the power 5. So we adopt these techniques in our method by replacing the tensor operations to sketching. Then we can drive Q times M features that approximate the neural kernels, whether it can be NNGP or NTK. And moreover, if coefficient decays, here C0, C1 decays very fast, we can get a more accurate polynomial approximation on F. Then, this can give a subspace embedding. Subspace embedding, which is the eigenvalues and eigenvectors are preserved. So this is the key idea. So to summarize, we do one-pass sketching algorithm on the polynomial approximation on NTK or NNGP. But this technique only applied to fully connected neural network when activation is homogeneous. And for generally, this cannot be available. But we can also approximate the feature map in a layer-wise manner. So consider the convolutional neural kernels, which include nonlinear mapping and convolution and poolings. And for convolution and pooling layers, we can find a trivial feature map. This is very easy and exact feature map. And for nonlinear activation, we can approximate the find feature map using the sketching algorithm. Okay. For one additional thing is that, so actually this method is based on the recursion of neural kernels. But so once we find a good feature map of those NTK and NNGP,
but we also find a good feature map of the product of those two corners. And the product of corners, which is in the low form, they involves in tensor product of order 2. So to avoid this, we apply additional sketching to approximate the product of those two corners. So this is one thing different from the one-pass sketching algorithm. Okay, so and we can analyze the element-wise error bound. Here we have a feature dimension m and m prime. M prime comes from the additional sketching for corner product. And since we apply the sketching in every layer for entire, and there is an L layer, we need to scale the error of each layer depending on the number of total layers L, so that this m and m prime depends on L. Okay. Yeah. So this approach is naturally applied to graph neural corners. So one different thing is for graph neural corners, there is a neighborhood aggregation layer. And once we have a good feature map, and it is trivially applied the neighborhood aggregation to this feature map. So we can obtain the corner approximation using sketching. Yeah, it's very trivial way. But for transformer, there is some challenges here. So we can actually apply our method for transformer, but in transformer there is a self-potential layer, and computing self-potential layer requires the cubic time in the number of input. So this can be another computation bottleneck. So to make a fully a linear time algorithm or linear time for low rank features, so this we can combine some type of approximation for self-potentials. And there are many variants of these self-potential approximations, and we hope we will work on this. So this is this is all for some techniques, and now I will explain the simple experiment. We do kernel regressions on the feature map, approximate feature map that on the 5-layer convolutional NTK. Okay, and we change the activations, including ReLU and Ricky ReLU, and some exponential type of dual kernel values. Okay. And the exact activation of those two methods are not known, but we can compute its neural kernels and its approximation. And here we observe that some scaled normalized Gaussian activations marked by the gold line shows the best approximation, best test accuracy. And this is because when we plot the dual activation function, dual functions, it decreases very smoothly. But if we approximate this gold line by some fixed degree, the coefficient decays much faster than other dual functions. So that this gives a better kernel approximations. On the other hand, ReLU shows the worst performance, and this gives the kernel function of this. Kernel function of this looks like this, and the Taylor's, when we do Taylor expansion on this blue dotted line, the coefficient decays very slowly. So this means that it is very hard to approximate given in the fixed feature dimensions. And compared to, so when we fix the dimension number 2 to the power 13, and we show the up to 100 speed up compared to the exact kernel, but there is a loss on test accuracy. So if we fit the test accuracy by reducing the training samples, and we can observe the 12 times speed up compared to the using the feature map compared to the exact kernel with the smaller test data set. Yeah, so this is very efficient. So we prove the efficiency of a feature map. So this is the simple result. And okay, let me wrap up this talk. Okay, so in this work, we propose how to compute dual kernels of the general activations, and using these observations, we can derive the neural kernels even without the activation formulation. We also propose a feature map approximation by sketching algorithm, and shows a subspace embedding for homogeneous activations when the network is fully connected, neural network. So as a future work, we can combine our approximation to self-potential approximations. Yeah, actually, recently we do some
efficient self-potential approximation based on kernel density estimations. So unlike other self-potential approximation, our KD-based approximation gives a spectral error bound. So we can combine both methods to find some good feature map of infinite width transformers. And we also can apply our method to infinite width and infinite depth limit of kernels. Because our method, we consider the depth is constant and look forward to extend our work on the infinite depth too. Okay, that's all for today's talk. Okay. Yeah, I'm happy to take also any questions.
So I have one question. So, because for transformer cell attention, when you have the submax, there's no way you can get the closed form for the like a NNGP kernel or NTK kernel.
Yes.
So in Neural Tangent, what we did is just using like a linear, replace the submax by the linear function, and then we can get closed form. But it turns out that the accuracy is not very high in CFAR 10. I'm wondering what's your intuition about if you using sketching to do the self-attention, and do you think that the performance on CFAR 10 using transformer will have some boost?
I expect if the transformer, the exact transformer work well on Cypher 10, and maybe I expect its feature map it also works well compared to this result on the convergent NTK.
I see.
And I think there is some deep network, including self-attentions, are pretty works well for image classifications, like there's also a model called T2T model or something like that. That is outperforms than the just convolutional neural network. So yeah, we can expect that.
Yeah, that would be super interesting, because when we just use the linear attention,
yes,
then the performance of a transformer is just the same as a full condensed network, and much worse than a convolutional network.
let's see.
Yeah. So if able to approximate the submax, that will be help us to understand whether this gap is due to the nonlinearity of the transformer.
Yeah, we hope. Yeah, we hope that these two feature approximations can be combined. And yeah, but we need to verify the performance is indeed improved or not. Yeah, it is. Yeah.
Cool. Thanks.
Thank you.
No other questions. Let's thank the speaker again.